Hello everyone. Chapter 3, Lesson C. This will actually be part 1 of, I'm thinking, 2 parts. In part 1, that should be a part 1. In part 1, we're going to cover these first 2 topics. And in this video, I will not be covering, but will, in part 2, cover the second 2 objectives. So today we're going to recognize special right triangles and their properties, as well as solve some word problems involving right triangles using the idea of angle of elevation and depression. Last time you'd likely seen that would have been geometry, which for some of you may have been about a year ago, maybe more. For others, maybe sooner. I don't know. But based on your specific history in math, you might have seen a number of the items you're about to see in this lesson today. So let's go ahead and get started. Okay, so I wanted to start with some special right triangles. And the red triangle and the green triangle are actually very, very similar. One is just flipped on its side. However, I'm going to consider those two angles 30 and 60. And then the blue triangle is our isosceles right triangle, which is our 45, 45, 90. Now, we talked about these in the last lesson, and we spoke about the ratio of their sides. So just as a reminder, this leg here on the base will be 1/2, and this leg here will be root 3, provided that the hypotenuse is 1. Okay, in the green triangle, those sides will be flipped. This will be 1/2, this vertical leg, and we would have root 3, excuse me, that should be root 3 over 2. I goofed that up. But those two triangles are the exact same triangle, just on a different perspective. And then we've got our 45, 45, 90, which would be either 1 over root 2, which I prefer to use, or root 2 over 2. So let's consider the cosecant of 60. This is a bit of a review, but let's do it anyways. So the cosecant of 60 will be the same as 1 over the sine of 60. Okay, the sine of 60 would be opposite over hypotenuse. So the sine of 60 is root 3 over 2. Therefore, the cosecant of 60 is 2 over root 3. Again, we could rewrite that in the form 2 root 3 over 3. Either of those two is acceptable answers. Okay, how about the tangent of 45? Well, the tangent of 45 is the opposite, the side across from the angle we're referring to, over the adjacent. So opposite over adjacent, those two are equivalent, so the tangent will be 1. Anytime you see a tangent of 1 or -1, you should be thinking pi over 4 or 45 degrees of some reference triangle. We're going to talk about that in part 2 of this lesson. Okay, the sine of 30 will be the opposite over the hypotenuse. So the sine of 30 would be 1/2. Okay, so let's go ahead and get into evaluating trig expressions that can be done quickly using the unit circle. Evaluating trig expressions can be done quickly using the unit circle, which is an implementation of these special ratios. So the more familiar you are with the unit circle, the better off you're going to be. What if the triangle in the question is not a special right triangle, or a triangle that we've seen in the unit circle? Like this, for instance. This is not a scaled version of a 30, 60, 90 or 45, 45, 90. For example, I'm going to take the triangle from above. Let's say this angle looks like it might be 30 degrees, but I'm not sure. It looks like it based on the diagram, but I can't trust it. I have to use the numbers. So if I have a 30, 60, 90 triangle, then this would be 1/2, this would be root 3, and the hypotenuse would be 1. Now, I don't see the same ratio of 1/2 to root 3 here, so this is not going to be a 30, 60, 90 triangle. What I can do, though, in order to find the sine, cosine, and tangent is, of course, I don't know the measure of theta, but it doesn't really matter in this case, because to find the sine of theta, I just need the opposite and the hypotenuse. Well, I don't have the hypotenuse, so I can use what's at my disposal is the Pythagorean theorem. A squared plus b squared equals c squared. This is something that you should be very comfortable with, and you are going to use very, very much in this course and in others to come. So I'm going to add 9 and 16, gives me 25. That's c squared, therefore c is 5. Therefore our hypotenuse is 5. And now I can go ahead and write out all 6 ratios. Sine would be 3/5. Cosine is 4/5. Tangent is 3/4. And then our reciprocal functions follow suit. I'm just going to reciprocate each of these answers, and I'll get my sine, cosine, or excuse me, cosecant, secant, and cotangent of those values, or of that angle. All right, here's another example. Now, a 3, 4, 5 triangle is one that you need to be very comfortable with and familiar with. This is a Pythagorean triple. Here I have another Pythagorean triple. Some of you might already know this, but a 5, 12, 13 is a Pythagorean triple, provided that the 13, of course, is the hypotenuse. So I'm going to confirm that. So 25 and a 169. Oops, I'm sorry, not a 169, a 144 is equal to c squared. So 169 equals c squared, so 13 equals c. Okay, so now I can find the sine of alpha. This angle here is alpha. Sine of alpha is 5/13. So the cosecant of alpha is 13/5. The cosine of alpha is 12/13. So the secant is 13/12. The tangent of alpha is 5/12. So the cotangent of alpha is 12/5. Guys, that's how you use the Pythagorean theorem to help you find the 6 trig functions of a non-unit circle triangle. Now, triangles can show up in the unit circle and don't use special right triangles, but these in particular, it's useful to use the Pythagorean theorem. So let's go ahead and move forward and see what we got next. Okay, so a little bit of an overview of what we've just done, in addition to adding a different type of example to this topic. But at this point, we have a couple of tools available to us, and we're going to continue to add to these tools in order to help us find the 6 trig functions of a right triangle. So the Pythagorean theorem, it's number 1. It helps you find the third side. Then you can find all 6 of the ratios. And then SOHCAHTOA. And SOHCAHTOA is just the process of opposite over hypotenuse, adjacent hypotenuse, opposite hypotenuse. Now in example 2, let's use these 2 tools and sketch a triangle corresponding to the function with an acute angle theta, which means if this is an acute angle, that means we're going to be in quadrant 1, okay, at all times for these examples. Then what we're going to do is we're going to find the cosine of theta. Okay, so let's sketch each of the following and put it in the appropriate quadrant, and then we will find cosine. So the cotangent of theta equals 5. That tells me that the tangent of theta equals 1/5. So if I sketch in quadrant 1 a tangent of 1/5, okay, here's my right triangle, there's my angle measure, opposite, adjacent. What I need to find in order to find the cosine of theta is first I need to find the hypotenuse, and then I'm going to take 5 over the hypotenuse. So the cosine of theta is going to be 5 over whatever our hypotenuse is. So Pythagorean theorem would tell me I'd take 1 squared plus 5 squared, set it equal to c squared. That's going to be 26 is equal to c squared. So the hypotenuse will be square root of 26. And there you have it. There's the cosine of theta if the cotangent of theta is 5 and the angle is acute. Let's look at example 2 here. Okay, example 2, the sine of theta is 3/8. So opposite, hypotenuse, here's theta. I got to find my adjacent side in order to find cosine. But I do know that the cosine of theta will be whatever that length is over 8. So Pythagorean theorem would tell me that, I'm going to call this, just for a moment, I'm going to call it x. And that's going to equal 8 squared. So that's x squared plus 9 is equal to 64. So x squared is equal to 55. Therefore, x would equal the square root of 55. And there's the cosine of theta. All right, let's move on to our last example. The tangent of theta equals 1. We've seen this just a moment ago come up. Tangent of theta equaling 1 should make you think 45, right? So if the tangent of theta equals 1, 1 over 1, or 10 over 10, or 100 over 100, our tangent is 1 because the opposite over the adjacent is equivalent to 1. So if I want the cosine, okay, careful with this, I would likely, if I were you, I wouldn't use big numbers like I chose to use. I would use the number 1. Your answer will reduce to the same thing. However, it will just save you a lot of time. So Pythagorean theorem would tell me 1 squared plus 1 squared is equal to c squared. So that's 2 is equal to c squared. So c is equal to square root of 2. And therefore, the cosine of theta is equal to 1 over root 2. There you have it. Let's continue on. Okay, very interesting example here. Find now the angle, acute angle, theta, in radians and degrees without using a calculator. So what I'm going to do is, again, I'm going to sketch in the first quadrant each of these examples. So let's sketch sine is equal to 1/2. Okay, sine equal to 1/2. That's 1, that's 2. This would be a theta. That would make, using Pythagorean theorem, just trust me, this would be root 3. Okay, so let's do the second one. Secant of theta equals 2. That means the cosine of theta would equal 1/2. So if the cosine of theta equals 1/2, here's theta, here's 1, here's 2, here would be root 3. Let's stop here and do both of these problems. What angle would we get for part 1? Well, the only way I can get this is by knowing my special right triangles. This is going to be a 30, 60, 90, and the 30 is always across from this side, right? So if you've got this this ratio of 2 to 1, that's the hypotenuse to the short leg, and the short leg is always across from the 30. Now we know that that is pi over 6 in radians if we were to convert it. Now for number 2, we have the same triangle flipped on its end, therefore theta will equal 60, or pi over 3. Okay, let's look at the next one, number 3. The tangent equals square root of 3. Okay, we're in quadrant 1, nothing's changed there. Opposite over adjacent, that's going to make this side a 2. Okay, which angle will that be? That will again be just like number 2. Theta will equal 60 degrees, or pi over 3 radians. Okay, cosine of theta equals root 2 over 2. Let's plot that one. Okay, cosine of theta equals root 2 over 2. Using Pythagorean theorem, this is an interesting example. I'm going to use Pythagorean theorem. So square root of 2 squared, I'm going to call this y for a moment, plus y squared is equal to 2 squared, the hypotenuse. Squaring the square root of 2, I get 2. Y squared and 4. So y squared, if I subtract 2 from both sides, is 2. So y equals square root of 2. Okay, now if you look at that, that is a 45, 45, 90 triangle, right? Those two legs are the same length. Therefore, theta equals 45 degrees, or pi over 4 radians. Okay, cotangent, root 3 over 3. So if the cotangent is root 3 over 3, then the tangent is 3 over root 3. So let's sketch that out. 3 over root 3. Okay, now let's do Pythagorean theorem. So 3 squared plus root 3 squared is equal to c squared. So 9 plus 3 is equal to c squared. So c is equal to the square root of 12. Okay, now it might be hard for you to see this, but this is a 30, 60, 90 triangle, and let me show you why. All right, let's call this 1 and 2 and root 3. Okay, so theta, this is a similar triangle. Clearly one is scaled to a different size. Okay, but the both of these are the same. Now watch how I do this. If I take this triangle, which let's call it sides 1, 2, and root 3, those sides should correspond to each of the corresponding sides in the other triangle. So that would be root 3 over 3 and 1 over root 3 and 2 over root 12. Okay, if I were to cross multiply any of these, I should get an equivalent answer. Really what I'm doing here is I'm multiplying each by root 3. Okay, in order to get each of the equivalent sides. So therefore, or corresponding sides, excuse me, this angle right here should be 60 degrees or pi over 3 radians. That's an interesting question there. Okay, cosecant of theta is root 2. That means the sine of theta is equal to 1 over root 2, which should immediately tell you pi over 4 or 45 degrees, but I will plot it just to be safe. Okay, so if the sine of theta is 1 over root 2, 1, here's theta, 1 over root 2 over hypotenuse. If we use Pythagorean theorem, we would end up seeing that that side is also 1, telling us we've got ourselves a 45, 45, 90 triangle. Okay, guys, some good stuff there. Let's get on to our last few slides here. All right, so let's get into the word problem. We're going to use this idea of right triangle trigonometry, and it might be a little bit foreign or maybe not. We're just dusting off some topics that you've seen in basic geometry courses. So let's go ahead and get into it. I've got a diagram here of a tree and an angle of elevation. So before we do the problem in actuality, I'm going to talk a little bit about angle of elevation, angle of depression. This angle right here and this angle right here, they will add up to 90. Now, if I were to sketch a horizontal line, let's say that's parallel to this line here. This green angle is the angle of depression. So imagine a little bird sitting up here, right? That's an awful bird. But that bird sitting up there, if it looked down at this person on the ground, it would have to depress its vision from here and rotate it down. That's angle of depression. Whereas this person on the ground is looking horizontally to the plane or to the ground or grass, but has to elevate, right? It has to elevate their vision up. Whereas, again, the bird had to depress their vision and bring it down to see that point on the ground. But the nice thing is that the angle of elevation and the angle of depression are always equal in measure. So it doesn't matter which one you consider when you're looking at the triangle. So if I were to draw a second triangle right here, this triangle is equivalent and congruent in every way to the triangle that we are going to use to solve this problem. So let's sketch out the triangle now that I've totally butchered it. I've got a 50 here. I've got an angle of elevation of 71.5 degrees, and I want to know the height of the tree. Right, the height of the tree. So what I can do is I can consider what sides are given to me. So here's my angle, right? So this would be, 50 would be my adjacent side. My hypotenuse is over here, and I don't care about the hypotenuse. It's not doing anything within the context of the problem. I'm not looking for that length. That length is not given to me, so I don't care about it. So I'm going to just knock off the hypotenuse here. What I am looking for is the opposite side. So when I see that I'm looking for the opposite side and I'm given the adjacent side, the O and the A tell me TOA, and TOA tells me to use the tangent function. Now the tangent function's input is always an angle. So the tangent of 71.5 will be equal to the opposite side, which is y, over the adjacent side, which is 50. I'm real close here. I can now solve by multiplying both sides by 50. So if I multiply this side by 50, the 50's reduce. So I multiplied that side by 50 as well. And what I'm going to end up with is y, and y is the height of the tree. Now, when you do this calculation on your calculator, make sure you are in degree mode. So again, reminder, press the mode button. Make sure you're not in radian mode, but that you're in degree mode, and take 50 times the tangent of 71.5. And it looks like we get a height of 149.434. What are we measuring here? Feet? Feet it is. Here you have it. That's how you use right triangle trig to solve a word problem. We got a couple more with a little different flavor to it, but that's a good start. All right, let's move to the next problem. Okay, another word problem here. You are 200 yards from a river. Let's draw you. I'm not real good at drawing, so I'm just going to draw a face here. And I'll draw a stick figure. Here you are, just standing there with your arms in the air. You are 200 yards from a river, but you choose not to walk along the path of that 200-yard line. You choose to take the shortest distance to, I don't know, this must be where the pull-up bars are, and the jungle gym. Here's our monkey bars. You want to go get a workout, and you don't want to walk along the shoreline because apparently this river is full of piranhas. So you choose to take this distance here. Okay, well, what we're looking for is we're looking for this angle. We don't know what it is. Likely, you guys, if you don't have the ability to use your calculator to find an angle, I'm guessing this triangle is going to be a special right triangle. So I'm going to re-sketch it here, and I'm going to show you a little trick we like to use when working with special right triangles. Okay, what is the greatest common factor of 200 and 400? Well, the greatest common factor is 200, so I'm going to divide out 200. And guess what this turns into? A 1 and a 2. That should look familiar because if I use Pythagorean theorem, this would come out to be a square root of 3. And in a 1, 2 square root of 3 triangle, the angle across from the 1 is always a 30. Okay, if you've got it down to its bare bones ratios. So therefore, theta in this case is 30 degrees or pi over 6 radians. Okay, let's move on to the last couple of pages here. All right, here we have it. This must be a real special place because, I don't know. This is a wild word problem, but whatever. The Johnstown Inclined Plane in Pennsylvania is one of the longest and steepest hoists in the world. 35.4 degrees doesn't seem that steep, but trust me, it is. The railway cars travel a distance of 896.5 feet, like you can see here in the diagram. Okay, going up this incline of 35.4 degrees. Okay, rising to a height of 1,693 feet. Okay, so probably a little over a quarter of a mile. Okay, above sea level. Okay, so let's find the vertical rise of the train cars. So now consider that this 1693.5 is not the vertical rise. It is the height above sea level. So I don't know where sea level is. Sea level could be lower than this point right here, right? And likely it is. So let's go ahead and find this height. Let's call it y. So y is across from our angle. So it's going to be our opposite side. And 896.5 is our hypotenuse. So opposite and hypotenuse are communicating the desire for a sine function. Okay, so the sine of the angle is equal to the opposite side over the hypotenuse. And I'm going to solve for the opposite side, or the height that the train cars have traveled, by multiplying very similarly to the last problem these two things. 896.5 times the sine of 35.4. 896.5 times the sine of 35.4 is equivalent to a vertical rise of 519.326 feet. Okay, so very interesting. Find the elevation of the lower end of the inclined plane. Okay, so if we're to think about this, let's try to make a visual. I'm always better with visuals. Here's sea level. Okay, here is the top of the building with the flag on it. Let's make it appropriate. Gotta have some detail. There we go. All right, so I know at the top of this incline, the height above sea level is 1693.5 feet. I also know that the height that the train cars will rise as they go up is 519.326 feet. What we're being asked here is the elevation of the lower end of the inclined plane. I want to know how far above sea level the lower end of that inclined plane will be. Well, what we'll do is we'll take 1693.5. We're going to subtract 519.326, and we're going to get our answer, which comes out to be, get out my yellow pen here, 1174.174 feet. All right, there you have it. One more example, you guys, and we'll be off and at 'em to part 2. Okay, as you look at this diagram, you should actually feel very confident in the limitations to this problem and what this problem could ask us. Okay, I'm not even going to read the problem yet. I'm just going to look at this, and I'm going to assume that whoever built this tower, right, whoever constructed this, did so in a sound engineering way and made that 90 degrees or perpendicular to the ground. When I see that both sides of this triangle are the same, I see that both angles here are the same, which would mean that this has got to be a 45 and a 45. And because I know the 1, 1, root 2 triangle, which is similar to the 1 over root 2, 1 over root 2, and 1 triangle, I know that this side, either using Pythagorean theorem or proportional sides in similar triangles, would be 50 root 2 feet. So let's go back and read the question and see just how simple this can be based on that understanding of that special right triangle. A zipline steel cable is built out in the country. Look at that. The high end of the zip line is attached to the top of a 50-foot tower, while the lower end is tethered 50 feet from the base of the tower. How long is the wire? Hey, we did some math. We figured it out. It's 50 root 2 feet long. That's bigger than 50 feet. You can multiply 50 times root 2 and get that in an approximate form if you would like. This is an exact form. Okay, what is the angle of depression of the wire? Okay, now, this is interesting. The angle of depression is not this angle. The angle of depression is this angle. But it just so happens that they are congruent. So this is our angle of depression. This right here is our angle of elevation. Angle of depression will be 45 degrees. All right, guys, that is lesson C, part 1. Have a great day. See you next time.